Hello and welcome back to another episode of Programming on the iPio channel. I am iPio. Okay, so the ASCII table. The ASCII table is a 7-bit representation of printable characters. So if I go right line, because there are only binary thingies in the computer, which is fairly obvious, I think. But how does even? If I go right line character A, right? It writes the character A, but how did it know what A is? Right? How did A get transported through? And A is a character, so I can cast this to a character, kind of make it an A, which is fine. I can also go ahead and say, well, print the number 65, which is also an A, and 66, that is actually a B. Now, the number 0 is also in there, and it's not all zeros. That is null. The number 0, and then I need to cheat a bit. So 0 binary, and then you need to navigate to the number 0. I'm looking at so if you Google ASCII table, you can find it, and what you're looking for is the 7-bit ASCII table. Don't go 8-bit. That way lies madness. Okay, so the you can see the ASCII tables in rows and columns with bit 1 to bit 7, and they're counting from the right. So bit 1 is the least significant. To get to number 7, so you're going in row 000, but the column is the column 3 actually, so it's 011. This 7-bit representation is it should be 0. Yeah, see, it's 0. And the great thing is that it's now easy to count up from that, because the character for 1 is just the next one down, essentially. So these 3, I'm not allowed to put comments in here, right? Am I? No. So the final 3 is the column. These 3 are the column, and this one is the row. So you're kind of going, how to write this? Yeah, so, well, row, 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 row. And then you go column, 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 0, 1, 0, 1, 1. And you can see these add up to 7-bit. So ASCII is 7-bit. The 8th bit was used to extend ASCII for local characters, like German characters. This one. Ah, come on. I know you want it. Yeah, that one. That one's a German character. It might not be exclusively German, but in any case, this character here isn't in ASCII 127, like a 7-bit ASCII. In the values from 0 to 127, it's not in there. It is an extended table if you use ASCII. This is probably just using UTF-8, which is way better. It's UTF-8 is, or the whole UTF thing is the realization that just screw it, just number everything. Whoever wants any number, we just add the number, and eventually everybody will get bored and stop adding things. And this is where we are now, which is great. It's actually really good, because, yeah, you should be UTF-8 compatible. If you're not, ASCII 7 is also UTF-8 compatible. You should really use ASCII 7. if you do anything that you want to be compatible to anything else, you should use ASCII 7, because that's the one that's the least likely to break. So like transmitting stuff over the internet. ASCII 7, least likely to break. Okay, so what's in here? We know that this one is 0. Yeah, and I should count out. I should count out the rows. Yeah, let's go. That's row 3. That is row 2, row 1, row 0, and it goes up to 7. 4, 5, 6, 7, and then these count. These are actually 15 now, I think. No, it's 16 because the 0 counts. 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, now we have to get the, I should have just written 0 here. 1, let me insert. So the next one is 1, 0, full 1, 1, 1, 1, 1, 1, 1, 1, 1, and here's where everything repeats. So let me just grab all of this stuff and paste it in here. No. Okay, select everything, paste it. Okay, and these are all 1 now. And this is how you do ASCII. Okay, so we know that this is the value 0 and continues 1, 2, 3, 4, 5, 6, 7, 8, 9. What comes after that? Okay, and there come special characters. Let me check that. Oh. Okay, so the comments might screw up everything. Just realized that. And the question mark. Just remove that so that the underline is gone. Okay, so we should be able to write this value here by writing 111. See, question mark. We did it. Where's the X? The A. The big A is 65. What's 65 in binary? No clue. It's in column 4, so it's over here. And it's 100. And it's the A. And A goes down here. A, B, and so forth until it hits, what's the last one on the column? O. And then goes over 5, it starts with P. God, I'm a child. Okay, row 10, this row here should be, is that that? Yeah, that's that. Okay. And then the next row over, oh no, this is the add sign. Okay. And this is actually the header. Right. The next row over, like here, it starts with, which one is that? Is that this one? Continues with lowercase a, and then kind of repeats. Why is there a B? It should be an A. Okay, so this one's 65. The distance between the big A and the small a is the same. That's for everything else as well. So if you go character well, if you go integer a cast to integer, this is 65. And this is a totally different value. So this is for a and this is for a. Yeah, that's right. So write line 8 as a character. Casting is pretty hard because it just says use these. Well, on a value type it does. Use these bits like the other bits. So the bits that make up 65 is that one, and then there's bits that make up the A. What I want to get at is we have an integer for B, and that is equal to the to B cast to integer, and then we have the lowercase b, which is the distance. You can see that the lowercase a is bigger than the uppercase a. So there's a distance between the two. So the distance between these two, if you add that distance to b, you get lowercase b, right? So if I print lowercase b now, I have that value because the distance, that's just how the ASCII table works. Actually remove these two. You can work with these distances. And the idea is that this will be easy to remember. All of these values up here are basically special characters. This one is a space. Yeah, and it goes on like that. Okay. There is there's a different way to do that. If you go character, well, we can also remove that. Character B is B, which should be a character. I can't do that. Okay. There is a function called toLower. It could be on string though. String B. String, trying to break it. I never do that normally. Where's the toLower function in C#? toLower, yeah. And then though, we only want the first character. That was complicated. So it does the same thing kind of. It's just easier to use, and you basically never work on single characters. What else? I think there is a is it on character? Oh, you can do it toLower on a single character. Okay. Trying to see if there is a is symbol is printable or something. Definitely one of the is control. Yeah, if it's a control character, we don't want to print it. Okay, because what I want to do now is go through the ASCII table. You're just going to use a for loop for integer e is 0 as long as e is smaller than 255, which is 0xf. ff. Oh no, 7f actually. Do we want to print 7f? No, smaller than ff is correct. Is it? What's the next value over? 7 is 1, F0, F0. Because it's 1 bigger than, if you look at the values, 1, 1, 1, 1, 1, 1, 1, that's the biggest number. This one we want to print. And this one is the 8-bit value that we don't want to print. Yeah, so that one is 8, that's not F. It's 80, of course it is. Okay, phew. Plus plus I. Okay, so yeah, we're iterating through all of the ASCII values. And so each row we want to print. Actually, we shouldn't iterate like that. Well, if we don't, we would bit fiddle. Tough choice. Okay, let's just go console.writeLine and be brutal about it. Plus, I'm using pluses here instead of string interpolation just for compatibility's sake. Let me know if you actually have, let me know if a string like that let me know if your compiler accepts the string, if it compiles that. If your C# version accepts that, then I'll switch and I'll do that instead. So what I want to do, I wanted to have the character C, and that one should be the character cast of I. And if C is, if character is control, let's control C. So if C is a control, then we write something else. And if it's not a control, we write whatever's in the ASCII table. And the thing that we write is CTRL or something. CTRL, and then in the other case we just write C. Let's see what the result is. Nothing compiles because I have loads of crap in here. Okay, see? So the first ones are all control, then the space follows, and the remaining ones are not controls. It goes up to 127. Oh, that's delete, I see. Yeah, that's a control. Isn't pretty is not a table. We wanted to have an ASCII table. So let's go and have an ASCII table. Okay. Let's only ever write, and let's not write I. That's the first thing, right? We only write the value. Okay, when do we write line? We write line whenever we bits 1, 2, 3, 4. That's my brain is starting to leave the building, so I need a break. But this is essentially 15. So if it's divisible by 16, we want to write a new line. So if, oh yeah, inside the loop, of course. If I is divisible by 16, then we go ahead and write line a new write line. Okay. Other than that, we just write. Oh, we should include spaces, by the way. Otherwise, it'll look clumped up. And why is C not acceptable? Probably because something's messed up above of it. So just console right line. Right line. Okay, yeah. So what this one is the modulo operation. It's like in elementary school when you first learn division, you divide it and it had a remainder. And if it doesn't have a remainder, then it's awesome. And this is the modulo. That's basically modulo, what you learn in elementary school. So if you divide 4 by 3, you get 1, rest 3. So there's a rest of rest 1, of course. So there's a rest, right? And if there's no rest, if the rest is exactly 0, this is what this equals 0 checks. If there's no rest, it means it was divisible, right? So 3 divided by 3 is 1 because it fits once, and the rest is 0. So there's no rest. And that's actually what modulo checks. So if it's divisible by 16 and has a rest of 0, that'll create a new line. So 0 divided by 16 has a rest of 0, so it'll create a new line that I didn't want, but too lazy to optimize that away. On 15 is where I'm doing this wrong. I'm going rows now because it's 15 rows. I have to break on column, right? So I need to break on 8. Yeah, because it's 0, 1, 2, 3, 4, 5, 6, 7. And then if it's 8, I need to insert a new line because the 8 goes in the next line. That should be it. Yeah. No, it's not. It kind of is what I wanted, but see, the thing is I flipped the table. So 15 is actually correct because I'm counting from that direction, but I'm flipping the table doing that. Well, modulo 60 then. I'm sufficiently satisfied. Check out the ASCII table on Google. You'll see how this isn't what you see because I just flipped it. Actually, it's just output this. Let's just output a C for control, I guess. Oh, we can go CTRL. Still go control. Control, go CTR, and have this one have 2 more spaces. That'll line up perfectly. Absolutely. And then we go and insert another new line down there. Beautiful. Okay, so this one is exactly flipped like that. Yeah. See how this row up here needs to be there. This is how this is flipped. And if you Google for an ASCII table, you can see that this is the case now. There's the P, there's the lowercase a, here's the uppercase A, and this is the ASCII 7. You can print the table like that. You might want to prettify this like a lot. I'm not going to. I think I talked enough about ASCII for now. Yeah, and that's ASCII 7. And this is how characters work in the computer. Next time we switch topics from data types and number systems into something else. I should check that. What's the next slide is? Oh, it's still on data types. Okay, it's some more about data types. I might skip ahead and see. These slides are awesome. It goes from these are data types into this is asymmetric encryption. Okay, right, we're doing asymmetric encryption next. Why not? Thank you so much for watching. See you next time. Bye.